Hi, today we are looking at significant figures and scientific notation. So we'll start with significant figures. So I'll often abbreviate these as sig figs, especially if on a quiz or test your answer is not to appropriate amount of significant figures. So then you can see what you need to work on. So what exactly are significant figures? They're the number of reliably known digits in a measurement. So in most cases we can count up how many digits are in a value from a measurement, and that's how many significant figures we have. However, if there is a zero, we don't always count them. So we'll talk about that next. So when do we count zeros as known digits or as significant? They count as significant if they're between numbers or falling after a number if a decimal is involved, or in other words, showing precision. So both of these examples have three significant figures. So for the first one, we have 405. So we've got 4 being significant, the zeros between the two numbers, so it's significant, and the 5 is a digit, so all three of these numbers are significant. So this has 3 significant figures. This one here, 2.40, the zero is showing us we have measured to nearest hundredth. So we once again have 3 significant figures here. We'd count our zero in this case. Where we don't count our zero is when they're used for placement purposes. So if it's used to get us to 1,000 for millions or tenth, in those cases we don't count them. So both these examples have just 1 significant figure because the zeros in these cases are for placement purposes. So this one would only have the 2, and this one would only have a 3. So this one, the zeros are to get us to a nearest hundredth. This one, for all we know, they just rounded the answer to nearest thousand. Now we can make 3,000 all 4 be significant if we put a decimal at the end, because that would mean that we've measured to that precision. But otherwise, it would just be 1 significant figure. So we want to do some practice questions. So how many significant figures in 3.14 seconds? So in this case, we don't have any zeros, so we can just count our terms. So we have the 3, we have the 1, and the 4. So we have 3 significant figures. Next one, we have 3.2604 meters. Now in this case, our 0 is between 2 other numbers, so we do count it. So we have a 3, the 2, the 6, the 0, and the 4. So we have 5 significant figures. Next one, we have 0.23 newtons. In this case, our 0 is there for placement purposes, so we only have the 2 and the 3, so just 2 significant figures. Next, we have 2,800 feet. So same thing as the previous one. Our zeros are there for placement purposes. We assume they just rounded to nearest hundred. So we have just 2 significant figures. Next one, we have 3.2300. So this one has a decimal numbers and then 0. So these zeros in this case are showing precision, so they will count. So we have 1, 2, 3, 4, 5 significant figures. Next one, we have 1 in scientific notation. If something's in scientific notation, everything to the left of the times 10 to the power of is significant. So this has 3 significant figures. Now some math rules for significant figures, as well as precision rules. If we're looking at addition and subtraction, our addition and subtraction, we are looking at precision. So we say if a sum or difference cannot be more precise than the least precise measurement. So if something is measured to, let's say, nearest 1,000, and something else is measured to nearest 100, our answer would have to be to nearest 1,000. Alternatively, if we're looking at decimal places, if we have 1 figure to nearest tenth, so 1 decimal place, another to nearest hundredth, so that's 2 decimal places, our answer would be to the least precise of those, which would be 1 decimal place, so nearest tenth. So an example of that would be if we have 23.4 plus 0.51, In our calculator, that gives us 23.91, but our answer would be 23.9 because that first term only had one decimal place, so our answer could only have one decimal place. Now we have different rules for multiplication and division. These ones are based off of our significant figures. So our answer will be to the same amount of significant figures as the number of the least amount of significant figures in our equation. So for example, if we had something of 2 significant figures multiplied by something of 4 significant figures, our answer would have to go to 2 significant figures. And here's an example of that. We have something with 2 significant figures, our 1.1, times something of 3 significant figures, which is 4.54. Our calculator gives us 4.994, but because our first term only had 2 significant figures, our answer has to be rounded to 2 significant figures, so it gets rounded up to 5.0. Now what happens if we have a question that has both addition / subtraction and multiplication / division? On one hand, we could utilize both those rules, but for the sake of simplicity, we will just follow the rules for multiplication and division, so fewest amount of sig figs. Now before we look at scientific notation, we'll look at some steps for problem solving, because you'll find that many of the questions in this course are word problems, so they take a bit of decoding to help solve them. So my steps for problem solving are: first, read the question. So read through it, understand what the question's asking for, and what the situation or context is. Second, reread the question and write down all the relevant values, because when you read through and find your context, you may find that some of the values they've given you in the question you aren't going to utilize. So you're just writing out the ones that are relevant. You'll write out the variable that goes with them and the units that go with them. We'll also write out the variable you're solving for. So now that you have the variables that you have and the variable that you're solving for, you can look on your formula sheet and see which equation has all of those. Once you've selected one, write out that formula. Now, in most cases, you'll probably have to rearrange the formula because what you're solving for won't necessarily be on its own already. So our next step would be to rearrange the formula to get the desired variable on its own. Now in physics, we often rearrange before substituting values in, because as we get to more complex equations, you'll find that you have variables cancel out. So having them cancel out as variables instead of, for example, multiplying them in and dividing them out later is fewer steps and a lot simpler. So once we have it rearranged with a variable on its own, we're going to substitute the values in and calculate our answer. We will then round our answer to a correct amount of significant figures based off the values that we used for calculation. And then we'll check our units and give appropriate units for the answer. Okay, so now on to scientific notation. So with scientific notation, if we're converting something into scientific notation, what we want to do is take a number and shift the decimal place to left or right until we get a number that's between 1 and 10. We'll then write out this new number, and to right of it, put times 10. The exponent on that will be equal to how many times we had to shift our decimal place. Now, the sign of our exponent is going to depend on which way we shifted our decimal place. If we shifted our decimal place to the left, our exponent is positive. If we shifted it to the right, our exponent is negative. So we'll look at some examples of this. So write using scientific notation. So we've got 0.00653. So currently that's not between 1 and 10. So we're going to shift our decimal over 1. That still is not between 1 and 10, so we'll shift it again. That would give us 0.653, which is still not between 0 and 10, so we'll shift it again. That gives us 6.53, which is between 0 and 10, so we'll write that. So we'll use that, and then we've shifted that decimal place 3 times, and we've shifted it to the right, so that's going to be a negative exponent. So we get 6.53 times 10 to the negative 3. Next example we have is 2080. Now one thing to note here is, based on sig figs, only the 2, 0, and 8 are significant, so when we change it to scientific notation, we'll lose this 0. Now when we shift this, our 0's here. Shifting it to here is 208, that's greater than 10. Shifting it here is 20.8, that's greater than 10. So we shift it to here, so we've got 2.08. And we've shifted it 3 times, so that's times 10 to the power of 3. Last one, we have 12.4. You probably won't bother changing something of this range into scientific notation, but we can see we would just shift our decimal by 1. So we get 1.24 times 10 to the 1. Now, we'll talk a little bit about notations, because not all things will use a notation we just went over. Some calculators, as well as a test bank for this course, uses different notation. So it can also be written using a slightly different notation. So instead of using times 10 to some exponent, it can be written as e and then that exponent. That is what the test bank for this course uses. Also, you'll find some calculators use that. Some calculators will use a capital E instead. Keep in mind when you see this, that is not natural number e. It is just telling you it's a number times 10 to the power of whatever is after the e. So I have a couple examples here. So if I have 2.43 times 10 to the 3, on our test bank for course, that will show up as 2.43 e and then positive 3. If I had 5.27 times 10 to the negative 4, the test bank for this course will show that as 5.27 e negative 4.